Hey guys, this is Professor Janacek, and I want to talk about directional derivatives of functions in several variables. Now, a directional derivative, this is the rate of change of a function f at a point, which we'll call AB, in the direction of u, which is a unit vector. So we must have a couple of things. First, f must be differentiable at the point AB. And then u, which I'll describe as having the components u1 and u2, must be a unit vector. Now, the definition of the directional derivative, notice first off the notation we're using. I'm using uppercase D followed by the function to denote the derivative of the function, as opposed to some notation you may have seen in the past. And we also have a subscript there of the unit vector. So it's uppercase D, subscript the unit vector of f on the point. Now, the actual definition is what it looks similar to the limit of the difference quotient. That's exactly what's going on here, just as you saw back in Calculus 1 when you first defined a derivative. So it looks very, very similar. And of course, in order for this directional derivative to exist, the limit must exist. So I must be able to find this limit in order for this to work. Now, I will also mention that this limit here is very difficult to compute for most situations. So we actually have a little bit of a shortcut for it. Turns out, here I have it again, we could actually write this as taking the vector where the first component is made of the partial of f evaluated at AB. The second component is the partial with respect to y evaluated at AB. And then we dot that with our unit vector, u1, u2. Now this bit right here where we're taking the first component is the partial with respect to x, the second component is the partial with respect to y, and then that actually is so handy that it has a special name. So when I take the vector based off of a function f, and it's again the first partial with respect to x for the first component, the second component is the first partial with respect to y, there we go. This is referred to as the gradient. And it has this nice little notation. It's upside down delta, Greek letter delta, and of course it does act on this function. So, turns out, if we want to go back and write the directional derivative of f at AB in the direction of u, we simply need to compute the directional derivative, or the gradient of f at AB, and we'll dot that with our unit vector u. So there you go. That is how we will compute the directional derivatives. Again, we will also need to remember how to determine that gradient. All right, so let's go ahead and jump down. There's some more we'll talk about in a bit, but first let's take a look at some examples. Example 1, let's compute the gradient of the function f of xy equal to 4x squared minus 2xy plus y squared, and we want to compute the gradient at -1, -5. So we're just going to compute the gradient on this first piece. So the gradient of f, first off, we do want to compute the gradient first, and then we'll evaluate it at the point. So remember, that is the first partial. Actually, let's go ahead and jot that down. Let's take the first partial with respect to x. So looking over here, treating y as a constant, the derivative with respect to x, we end up with 8x minus 2y. And the first partial derivative with respect to y, again, looking at this here, treating x as a constant now, the derivative with respect to y, we end up with negative 2x plus 2y. Now, if we evaluate this at our point, -1, -5, we end up with that looks like 2, and partial with respect to y evaluated at -1, -5. Looks like -8. And so the gradient of f at -1, -5 is the vector 2, -8. All right, well, that wasn't so bad. That's going to be the first step in finding the directional derivative. So let's go ahead and try a few. For the next few examples, we're going to let f of xy be 2x squared plus y squared, and we want to compute the directional derivative at the given point in the direction of the given unit vector. So for each one of these, we're given a point and a different unit vector. Notice all of these are on the unit circle. All right, so for each one of these, we will need to determine what the gradient looks like. So let's start with that. Here we have f of xy. If we want to find the gradient, that's just going to be the partial with respect to x first. Well, that's 4x. And then the partial, oops, let me write it properly. All right, the partial with respect to x is the first component, and the partial with respect to y is the second component. And now we're going to use that for each one of these. All right, so for example 2 here, we have the point 1, 0, and our unit vector is the vector 1, 0. Okay, so the directional derivative in the direction of u of f evaluated at 1, 0. Remember, this is going to be the gradient of f evaluated at 1, 0 dotted with u. So that means we're going to need to figure out the gradient of f. Well, the gradient of f, just x of x, actually we've already got the gradient, evaluated at 1, 0. So again, here's our gradient. Evaluate that at the point 1, 0. We end up with 4, 0. And so now we're going to take the dot product, and that, by the way, is a 0 of 4, 0, and u, which is 1, 0. So we have, remember how to take the dot product of two vectors. Oops. It's the product of the first components plus the product of the second components. Multiply, add, put it all together, we end up with 4. So the directional derivative is 4. Example 3, very similar. Now our point is 1, 1, and our unit vector is 0, 1. So again, in this case, our directional derivative in the direction of v of f of 1, 1, that will be the gradient evaluated at our point 1, 1, dotted with vector v. So that means we need to figure out the gradient evaluated at 1, 1. Again, we have our gradient up here, evaluating that at 1, 1. Gives us 4, 2. So we're going to take the vector 4, 2 and dot it with our unit vector there, 0, 1. And again, the dot product is the sum of the products of the components. The first components with the second components, and it looks like that gives us a 2. Well, there you go. Okay, in example 4, we want to go in the direction of w, which is the vector square root of 2 over 2, square root of 2 over 2, and at the point 1, 2. All right, so the derivative of f at 1, 2 in the direction of w is the gradient evaluated at 1, 2, dotted with w. So our gradient evaluated at 1, 2, again, here's our gradient. Evaluate that at 1, 2. And we get the vector 4, 4. So we'll take the vector 4, 4 and dot it with w, square root of 2 over 2, square root of 2 over 2. So that gives us 4 times the square root of 2 over 2 plus 4 times the square root of 2 over 2, which is, let's see, that gives us 4 square root of 2. And there we go. There is our directional derivative of f at 1, 2 in the direction of w. Well, enjoy!